the Executive Director of the Energy Systems Integration Group. I want to welcome you to our monthly webinar series and give you a little bit of background on ESIG. For those of you not familiar with ESIG, we're a membership-based nonprofit organization providing our members with objective information and resources for renewable energy and energy systems integration decisions, peer-to-peer networking opportunities, information and knowledge sharing, and professional education experiences. Our most recent activity was our fall technical workshop in Denver in October, and our next activity will be the spring technical workshop just outside Albuquerque in March, which will be followed by an international energy systems integration workshop in London. These workshops deal with a full range of issues associated with integrating wind and solar into electric, gas, and thermal systems and coupling to energy-consuming infrastructures, especially electric transportation, buildings, and industry. Registration will open soon, and everyone is invited to attend. ESIG is a very unique organization, and I don't think you'll find anything quite like it anywhere else. If you're new to ESIG, I strongly encourage you to follow up with us if you like what you hear, and I think you'll be pleasantly surprised. You can find us at www.esig.energy. Okay, just a few logistical matters before we get started. First of all, the phones will be muted for the duration of the webinar to avoid unnecessary distractions. So please use the question and answer box on the lower right-hand side of the screen to submit questions, and we'll save 10 minutes or so at the end of the webinar for Q&A. We plan to wrap it up at the top of the hour, and an email with a link will be provided once the presentation and the audio file have been posted. I want to encourage any follow-up questions you might have. We will get those answered, and I want to ask you to keep an eye out for a SurveyMonkey questionnaire after the workshop, which will have some questions for you from Ryan. Your answers will help NERC moving forward in this area. Okay, so today our webinar is on the topic of converter-based generation model development and validation. Based on registrations, I would say it looks like a very popular topic. The webinar will feature Bob Zavadil, the Chief Operating Officer for the consulting firm EnerNex Corporation, and Ryan Quint, a Senior Engineering Manager at NERC. Bob is a well-known expert in electric power system issues for wind power plants. He supervised many wind integration and interconnection studies in both power systems, and he's worked with everyone from wind turbine designers and manufacturers to project developers and operators, transmission service providers, independent system operators, covers the gamut. Bob has over 35 years of experience in the industry, and he chaired our modeling and interconnection working group for many years. He's a regular participant in ESIG meetings. Ryan, in his role at NERC, coordinates a number of NERC technical groups focused on emerging risks, grid stability, inverter-based resources, and modeling improvements. Ryan has recently become an active participant in Joint Working Group 5 of the IEC SC8A. The IEC is an international standards development body, which I'm sure many of you are familiar with, covers a broad range of electrical and electronic industrial equipment sold in global markets. And SC8A is the subcommittee dealing with grid integration of renewable energy generation. Joint Working Group 5 deals with issues regarding the increasing amount of converter-fed resources on the grid. I would have to say that Ryan is becoming an internationally recognized expert in this area. I feel very fortunate to have Bob and Ryan here with us today. On a personal note, as I've gotten in the habit of doing, I took a look on LinkedIn last week, and I found out that Bob and I have only 3 shared connections, and I have 129 shared connections with Ryan. Since Bob is a long-standing friend of nearly 30 years, I can only conclude that he's not very active on LinkedIn, but I assure you that he is quite social. And since I've only known Ryan for less than 5 years, I guess that means he's very active on LinkedIn and also quite social. Anyway, I consider them both good friends, and it's a pleasure working with both of them. The purpose of the webinar today is to familiarize key industry players with the state of VG plant, model validation efforts, associated relevant NERC standards, and upcoming compliance requirements and schedule. So without any further ado, let's go ahead and get started. Bob will present the background and status of the VG model development and application effort. Ryan will present the evolution of NERC standards in this area and discuss the schedule for compliance. Bob, I'll now turn it over to you.
right. Thank you, Charlie. Just a question though. What is this LinkedIn you speak of? Do you have the link?
Right.
Yeah, I apologize. Get set in your way. So anyway, Bob Zavadil from EnerNex. I'm glad to be here again. I think it was November of 17 when we last spoke on this topic. And this probably won't be the last time as we go forward, as you'll understand by the end of the webinar.
Bob, you seem to be fading in a little bit, fading in and out a little bit, Bob. I don't know if it's a matter of how close you are to the computer microphone or not, but maybe you could try.
Probably. Let me contort here a little bit. Is this better?
I think so, yeah.
Okay. So I'm the opening act. I'm going to try to go quickly so we save enough time for Ryan because that's where the meat is. I'm going to give you a little backdrop, some observations from where I sit in this large puzzle. I want to talk about large signal versus small signal validation. I think Ryan will pick up on that, how we might go about doing that, and the challenges associated with it. So this is a growing concern, pun intended, because bulk renewable generation is growing very quickly. That is our focus today, although we can't forget that we have all this DER renewable stuff out there that is also on NERC's radar with regard to something to keep track of. So we're north of 100 gigawatts in the ground in the U.S., 10% of installed capacity, less on the energy side. But I would point out that with regard to liability concerns, I believe the capacity is more important than the total energy produced, because we need to understand the state of the system at any moment, and there likely would be some periods where a substantial amount of this, at least regionally, might actually be operating.
Bob, you're still fading in and out. You're still fading in and out. If you can get a little closer or speak a little louder.
Sorry about that. The other issue is that with the 100 gigawatts plus installed, if we think about the number of individual bulk-connected renewable plants, I don't have an exact count, but just penciling things, it's several hundred to more. And the reason that's important is when we talk about plant validation, it's not a type test on the turbine or the inverter, it is for the plant. Okay, so that scales the problem pretty quickly. There's growing awareness of the need for validating the plant models both statically and dynamically. Ryan will mention a couple of recent events back in 2016 where this was brought to the fore based on the after-action analysis. NERC had adopted Mod 33 last year. That puts the onus on the reliability side of the equation to have validated system models, which then transfers some onus to the folks that are connected to the bulk system to have their models up to snuff. And there's a few other things Ryan will touch on that are in the NERC space working in this area. So this all began, 13, 14 years ago as we saw non-negligible penetration of renewable generation, at least regionally, and identified the need to incorporate the behavior of these facilities into our, transmission studies that are really the foundation for ensuring reliability. And so that effort has been going on for some time. There's, into the second generation of these generic models that map well to the bulk system study tools, but there's much more work to be done on that front. So in terms of the dynamic model validation, we're talking about the behavior of the representation of the plant in these computer tools and the behavior in response to big events on the system. Okay, so when we say big events, large deviations in voltage or frequency, and how does the plant as an aggregate respond? Small signal validation we've been doing actually on the conventional generation side for some time, and that generally involves a small incremental change in, say, the voltage set point or the voltage target, and understanding, how the various elements of that system, respond to that command into a new voltage set point. And you can do the same thing frequency-wise by kind of fooling the governor and pretending that system frequency is declining or increasing and seeing what the response of the governor is. We can do that because we have a century of understanding synchronous genes. We've done a lot of small signal testing of exciters and governors, and we're pretty confident that we put all those together that we can capture the behavior of the aggregate system. For renewable plants, things are a lot more complex because of the power electronics. There's nonlinearities, limiters, special operational modes, those sorts of things where, depending on the vendor, depending on the arrangement, we can't be sure. So the graph there is, I made it up several years ago about how we might validate plant testing. We don't do stage fault testing, so in my opinion, monitoring at the point of interconnection with an instrument that has event capture at sufficient resolution is maybe the best way to go about this. So for PMU data, if we're talking PMU from the point of interconnection, we're talking about capturing first principle quantities, voltage, and the grid current injection. Field and reactive power are a little bit annoying because it's really the grid current injection that is happening in the model. And that's what we need to validate against. And we need to basically have a large disturbance. So the point is to have the monitoring installed with the vent capture and wait for things to happen because they certainly do. So it appears that just in general, this would be an approach for the large signal validation, especially for those plants that are already in the ground and operating. But there are complications. The specific events may be hard to replicate via simulation. The world is not so neat and clean as to have bolted three-phase faults to facilitate this. There's a lot of complexities with the model. Or the initial condition system state may be hard to put together. And then the origin nature of the system disturbances sometimes is hard to understand from a single point measurement. Probably more importantly, actual events will be asymmetrical, meaning we don't have those convenient three-phase faults. The tools we use, primarily PSSE, PSLF, and PowerWorld, are positive sequence only, so already we're kind of working with some blinders on. It's hard to model unbalanced events in detail. We can only do it approximately. And then events are infrequent, so we need to have this monitoring installed. We need to capture events and so that we have a cache of those that might be used when we get around to the validation. So that said, renewable plant model validation will grow in importance as Ryan will great in this presentation. We have these significant challenges, and in my opinion, the industry is kind of, especially in the renewable side, sort of waited for further instruction for some time. Although, certain reliability reasons have in fact required this for some time. But now we have NERC actively leading the industry forward, as I think you'll see from Ryan's presentation. So I expect the next 3 years to be different than the last two. And with that, I'll turn it over to Ryan.
Great, thank you, Bob. And thanks, Charlie, for the very kind introduction. I think Bob did a really excellent job describing, laying out the foundation of where we are, how we got to where we are, and also a little bit of where we're headed. I think each of the bullets on this previous slide there, we could probably spend a whole webinar talking about, the differences between electromagnetic transient and positive sequence RMS type simulations and the complexities in that and how we're going to have to deal with that moving forward. What I wanted to cover today, like Bob said, this is kind of a continuation of last year's November 2017 presentation, and I think we've come a long way just in 1 year. So what I want to talk about is some of the modeling aspects, some of the model verification aspects related to the NERC standards, and then look at where we're going and maybe how we're going to get there, and kind of think a little bit outside the box. So that's what I'm going to cover in my presentation today. I've got to give the disclaimer up front. I don't work in compliance. This material is not intended to be compliance guidance. Its sole purpose is to describe the technical aspects of modeling and verification of these types of resources. So if you do have compliance questions, feel free to reach out to me or to the NERC compliance department directly, and they can help you a little bit more concretely from the compliance perspective, and I'm going to cover some technical aspects today. So we've seen this slide before in the past. Hopefully everyone's somewhat familiar with the NERC reliability standards, and particularly the NERC mod standards. And namely what we're talking about here is mod 32, which is the data collection standard that gets the data to build the interconnection-wide base cases, which sort of act as the foundation for all modeling, even localized modeling after that, from the positive sequence RMS simulation approaches. Mod 33 is the system-wide validation of once you've got all those models together, how well do they accurately represent reality from a system-wide perspective. And then you have the individual modeling standards, modeling and verification and testing standards, which are mod 25, 26, and 27. So I'm not going to go into a lot of detail on each of those standards. We did that at the last year's presentation. These standards are now becoming in effect and being implemented and addressed by the applicable entities. And so we're seeing a lot of understanding and education across the industry on each of the standards, which is great. So a lot of work's been done there. Of course, I think at the beginning we have to highlight a lot of the excellent work that's been done by the industry in the last year, in particular, two really excellent guidelines that were developed by the NERC Inverter-Based Resource Performance Task Force and the NERC Power Plant Modeling and Verification Task Force. Both of those are fairly large industry groups, multi-hundred members that have come together to provide guidance and recommended practices for, on the left there, how we want both power system connected inverter-based resources to perform and behave, and what are the characteristics of that performance when connected to the BPS, and then how to do the model verification and the testing for inverter-based resources there on the right. So there are links there, and these materials are posted online. There's also a set of links at the back of my presentation as well, but feel free to reach out to me if you have any questions on either of those guidelines. We also wrote a modeling notification in support of one of our NERC alerts, and I'll talk a little bit about that in one of the future slides. But we identified an issue with particularly solar PV plants, bulk grid connected plants, using a ride-through mode called momentary cessation, and we realized that that was not accurately modeled. And so we very quickly got a bunch of industry experts together and drafted up a modeling notification which describes in great detail how to model momentary cessation using the second generation generic renewable energy system models. Momentary cessation is not a recommended form of large disturbance behavior. It's not a recommended form of ride-through, but in some cases, legacy resources need to use momentary cessation or a program to do so, and the models need to represent reality, either current reality or proposed future states. And I'll talk more about the differences between those. So we did identify that particularly momentary cessation is not being modeled appropriately, and we have a gap there, and I'll talk quite a bit more about that. So in this presentation, we're all used to the power flow representation there on the left of either a wind plant or a solar plant. We then convert that over into a dynamic representation, and most of the presentation I'll be talking about are the RMS, positive sequence simulation type tools, PSSA, PSLF, PowerWorld, PowerTech, VNR, et cetera, that we're used to running in the transmission planning environment, where you've got a block diagram and a data sheet and you fill that out, et cetera. So we're all very much familiar with that. But what I want to start with is the timeline of models. So kind of the process of a unit, an inverter-based resource is going into commission, becoming an interconnected in-service resource, and then the expectations there for modeling. So in the very beginning, during the interconnection process, you sort of start with a feasibility study. There's very little information known about the plant. You may know the megawatt capacity you want to inject, and that's typically like a power flow study. And the TP and the PC sets fairly rigid requirements in their interconnection process on the types of information that need to be provided, and then they'll run some studies to identify any potential reliability issues. But typically that's a power flow type simulation. Then you get further along in the study process, namely to the system impact study, and you still have a expected or proposed plant design, but it's much more detailed, and you know a lot more about like the dynamics of the plant, the recommended control settings, things like that. And again, the TPPC are setting requirements on the type of data that needs to be provided. TPPC being the transmission planner, planning coordinator. Up until commissioning, that is an expected or planned design. And so when you get to the actual commissioning test, you then have as-built designs, actual plant information, impedance values, control settings, power plant controller settings, inverter settings, etc. And those may deviate from the models that were provided during the study process. And those updates, once that plant goes into commission, need to be provided to the TP and the PC as soon as possible per the standards. So any change needs to be provided with a model and needs to be studied very quickly. Mod 32, once that unit is in commission and producing power, Mod 32 is the annual case creation standard. So it's a regular data submittal process to build the interconnection-wide cases, which are used by essentially all transmission planners and planning coordinators as a foundation for their studies. And that should be the latest and greatest, most up-to-date plant data and models that are available. And Mod 32 provides the capability for the TP and the PC to review that data. And if they see any technical concern with that data, they have the capability to flag it, question it, and demand an explanation on why that data potentially doesn't look right. And that communication and that feedback is very valuable. And we don't see that leveraged as much as we wish we have since it did land in the standard. And so we're trying to figure out how can we leverage that a little bit more to have that kind of back and forth feedback on the quality of the models. Mod 26 and Mod 27 are what Bob kind of mentioned. I'll talk a little bit about. Those are the verification standards of actual plant performance, looking at either a stage test or a disturbance and comparing the model to that to see does it match. Again, the TP reviews the test report that's provided and the data submitted, and they can flag with technical concerns if they have any. And that should be the latest expected performance from the resource based on the latest test that was performed. And I'm going to talk in detail about Mod 26 in particular here in a second. But I will make a recommendation here that transmission planners and planning coordinators should be doing a detailed review of those test reports that are received. You know, line item by line item, looking at what data was provided, why was it provided, and do I have a sufficient amount of information to understand whether or not that model is verified. We have seen very successful implementations of that with transition planners, planning coordinators have very good feedback with the generator owners to understand what the model is representing and what it's not representing. And we have horror stories of the transition planner essentially signing off on anything with test reports that essentially say no model is provided for false reasons. And so we have the full spectrum of good and bad. We need to come to the middle and have a good understanding of what the expectation is there. When you get a test report, you should be reviewing it. And then Mod 33 is the overall system model validation. That's up to the planning coordinator to look at a wide area of performance. And if they can pinpoint issues with that performance, they can direct the GO to provide a data check, provide verified settings, et cetera, to make sure that they're getting their models correct. So going into Mod 26, I'm going to walk through the process of Mod 26 because there's a lot of confusion and it doesn't seem to be well understood in a lot of conversations that we have. So requirement 1, so Mod 26 is the excitation standard, essentially the reactive power voltage control standard. Mod 27 is very similar, the active power frequency standard. So requirement 1 is that each transmission planner provides the requested information to the GO upon request, and those 3 bullets there, a list of acceptable models. So the TP should be ready to give a list of acceptable models. So when the transmission planner comes to me, for example, and says, well, I'm getting models and they're not using the right models, I just point to R1, bullet 1 and say, well, you obviously didn't provide them with a list of acceptable models. They're required to use a model that's deemed acceptable by the transmission planner if that information is provided. Number 2, the block diagrams, the data sheets, and number 3, the applicable GOs, existing equipment providing the models for the other resources if needed. So essentially the TP is providing the data needed to be able to provide back verified models in the right format, the right level of detail, etc. R2 is really the crux of the standard where the GO shall provide a verified model, including documentation and data to the transmission planner following the specificity in attachment 1. And on 2.1 there is that each applicable unit that's subject to the standard shall be verified by the GO using models that are acceptable to the TP. So 2.1 has a list of requirements in it that describe what that verification looks like. And 2.1.1 is really the crucial one, documentation demonstrating that the applicable unit's model response matches the recorded response to a voltage excursion from a stage test or a system disturbance. That one gets a lot of attention, and we heard in Bob's presentation, you do various tests, and you see does the simulation match the test, and if it does, I'm good. I'm going to push the envelope here a little bit and kind of push the status quo, if you will, and say simply showing that you're demonstrating that a simulated response matches actual response for a bump test, a voltage step test or something, is insufficient in meeting the standard. And again, I don't work in compliance, but in my opinion, that's not enough, because that's not verifying that the model is accurate. And Bob will talk to that. Bob talked to that, and I'll talk to it a bit more. There is a lot more information and a lot more parameters that are not touched, particularly for inverter-based resources and the large disturbance behavior, that aren't even remotely touched for small disturbance type tests. And so you're leaving a lot of that model unverified without providing some additional documentation. It doesn't mean you have to go out and put a fault on every unit, but it does mean that you should be looking at the model, ensuring that the data is correct, and explaining why that you think that data is correct. I'll talk more about that. But there's a bunch of other sub-bullets there: the manufacturer, the model number, the type of control system, the plant volt bar control functions, the plant level controller settings, the model structure, why the model and the data are what they are, compensation settings if applicable, and then a lot of this is geared towards a synchronous machine, but it also applies to an inverter-based resource. Requirement 3 is that each GO needs to provide a written response to the TP if they receive any one of the following, and these are all written comments, written notifications. So essentially, if the transmission planner sees issues with the model that's provided by the GO in R2, the GO then has 90 days to respond back, and that response has to contain either a technical basis for why the data is correct, updates to the model, or a plan to perform model verification again. And I want to touch on these because they're pretty important in my opinion. Everyone always says, well, I can make sure the model initializes and make sure it has positive damping, but I can't do much more beyond that. And I argue against that pretty strongly and say, well, okay, the first bullet says, is the model usable? Meaning, does it initialize? Is it in the right format? Did I get everything I need? Can I use the data appropriately? We have a lot of folks who are using, say, PSLF receiving models in PSSE format. Flag that and say that's not usable. I wanted the model that's in the correct format, and help them, provide them with a template or a model structure or a GUI online that creates the model for them, because the GEO is not a model user. The GEO has the data, but is not a model user, and so it needs to be a collaborative effort to make sure that data is provided effectively and appropriately, and you have to help the generator owner get there. They have the data, they want to supply it, in a lot of cases they just don't know how. Number 2, the written comments, identifying technical concerns with the verification document. In my opinion, if the documentation is insufficient or leaves gaps, that's a technical concern. If there are errors in the data, if you can look at the reactance values of a synchronous machine and see that they're flipped, that's a technical concern. If you are seeing rides, if you received alert data that said, well, I go into momentary cessation at 0.9, and you look at the data that was provided for the test, and it doesn't show the VDIP parameter set around 0.9, that's a technical concern. Flag it. Send it back. And this is not happening, and this is what needs to be happening, is that we need a lot more rigor looking at the test reports and going through looking for technical concerns that should be flagged. In a lot of cases, it's just the generator owner and the transmission planner need to be communicating and to talk about what's the model trying to represent and why. And the last one there, written response indicating that a simulation doesn't match reality, and that's using actual physical data, sort of disturbance-based model verification. And that one's incredibly valuable, and I'll show some examples in a moment. R4 is also important. I've heard a number of times that, well, if I change a control setting, I don't need to do re-verification. I don't need to redo my model verification. And I'd argue that that's false. R4 explicitly states that each GO shall provide revised model data or plans to perform model verification of making changes to the excitation control system or the reactive power voltage control system. And there's a footnote there, and I've highlighted in red, including software alterations that alter excitation control system equipment response, a change in the voltage control mode, or exciter voltage regulator, reactive power voltage control settings changes. So when you go in and you change a large disturbance or a small disturbance setting or a control mode, excuse me, or anything that could change the response of that resource to a fault or a step change in voltage, updated model or revised model data needs to be provided, or you need to perform re-verification per the standard. And I don't think that's happening in a lot of cases. So there is potential compliance risk there on the generation side. So again, I mentioned this a little bit, but I want to talk a little bit more detail about what are the expectations, my personal expectations on if I were to receive a verification report from a generator owner, or if I'm a generator owner providing this information, what should I be ensuring that my consultant that I brought in to perform some tests is providing me so that we have clarity on what the model provides. So the first thing, what are the models being used and why? We saw that pretty commonly that a bunch of resources were using momentary cessation and using the REECB model. And the REECB model doesn't accurately represent momentary cessation. So right there you have a technical concern. You're using a model that doesn't sufficiently or accurately reflect what the resource is doing for large disturbance behavior. That's an automatic flag in my opinion. But so each of the models selected, REGCA, REECA, REPCA, whatever the model is you're using, should have a description of, okay, here's why I picked that model and here's what I'm representing. You should have very clear data sheets, every model parameter shown with the value that's to be entered, and an explanation or derivation for every single model parameter. Doesn't necessarily mean it has to be a test. You could have a commissioning test that gets you some of your parameters. You could have type tests, factory tests that Bob alluded to that kind of show some other parameters, particularly at the turbine level. You can have the verification test report itself that can get you additional parameters, particularly on the plant level controller, for example. You can show communications with the manufacturer, the equipment owners. So asking questions about, well, why are these parameters set the way they are? Provide me an explanation of why they are set that way. And maybe in some cases you're using engineering judgment of parameters like measurement time constants, things like that, things that are kind of more standard. You can use an engineering judgment for that. So the combination of all those, you should be able to describe what every parameter is and why. It doesn't necessarily mean you have to apply a fault or apply a step change and show and demonstrate a match, but you should be able to show verification in other forms. So you have small disturbance expectations, and you need to understand the model limitations and the capabilities of the models. There are things that are not modeled, and we know that, and that should also be described. And maybe that's coming from the equipment manufacturer saying, well, I give you a model, here's what it is intended to be used for, here's the extent to which you can use that model in simulation, and here's things that you can't typically represent. Some of the drivetrain dynamics, for example, on a wind machine may not be accurately represented in the generic models. They may be, they may not be, and we need to understand that. So we're used to seeing these types of simulations where you've got a small disturbance, a step change in the grid, and you're looking at a reactive power voltage performance, either a step change or an actual grid disturbance, and you're trying to find a match. And we see this very, very commonly. This is described in great detail in our PPMV guideline for inverter-based resources, but it doesn't account for those large disturbance behaviors. For example, what happens during a fault event, which is the vast majority of simulations we run in the transition planning world. So from a large disturbance testing perspective, the question that's out there right now is, do we have a gap? And when I refer to gap, I'm kind of describing that we have evolving technologies, evolving resources, evolving models, study needs, study approaches, tools. Do we need to consider evolving the requirements to meet these changes? And in my opinion, we definitely need to be considering evolving the practices that we use to ensure that the data is accurate, particularly for the large disturbance. And we've seen that at the NERC level, and I'll talk in the next couple slides about why we're coming on so strongly now, because we're seeing that the vast majority of particularly solar PV resources connected to the bulk power system do not have models that accurately represent reality. And again, there's compliance risk there, and I'm not going to go into that, but there's reliability risk. For those that are familiar with history, that's one of the causes of the 1996 disturbances. The model said that everything was great, and in reality it wasn't. We're in that realm right now, just in a different feel and looks different, feels different, but it's the same thing. We have models that don't accurately represent reality, and we've got a very high priority in trying to address that risk right now to try to get the models more accurate, particularly for the interconnection-wide studies. So here's a really good example from First Solar on their disturbance-based model verification efforts. Let's think back quite a while ago. Let's go back maybe a year or so ago. They had a grid disturbance fairly nearby, fault event, and they monitored the performance of their resource using a PMU at their point of interconnection. In the top left there, you can see the green is the measured response and the red is the simulated response. And you can see a very clear mismatch. And you can note that the resource, that's seconds on the axis there. So that resource went into momentary cessation, zero plant output for upwards of like 35 seconds before it began recovering active power output. Now, one, the model doesn't match reality, but two, that response is really bad, right? And we saw a lot of resources out there. And First Solar has done a tremendous job of monitoring the resources, ensuring that not only does the model match reality, but the unit is performing in a way that supports grid reliability. And we're seeing a growing number of success stories where we're seeing changes being made because settings were being implemented into the systems, into inverter-based resources with little knowledge on what's actually supporting grid reliability. If every resource drops off and doesn't provide power for 35 seconds, the lights go out. I think we all understand that in the transmission planning world. The lights go out if you cease injecting current for 1 second or half a second, depending on your interconnection. So 35 seconds is an eternity to a stability engineer, right? But the main thing there is that the model didn't match. So their first issue was, okay, I need to get that model to match reality so I can provide that to my planner so they're aware. And you can see there in the bottom left, they were able to modify some settings in the generic model being used, and they get a nearly perfect match. You got a little bit of mismatch there on the end, and that's due to some partial tripping of individual inverters within the plant, and we don't account for those in the positive sequence simulation, the generic models. And so we sort of expect that, and that can be explained. But that match there on the bottom left there is pretty great. But the success story is in the right side, where they did a performance update and a model update that followed that, right? So they said, well, 35-second momentary cessation is no good. We don't want that. We're going to change our operating mode. And you can see there the plant output drops when the fault occurs, as to be expected, whether you're in some type of reactive current injection or a very short duration momentary cessation. That response looks a lot better. And we saw the unit go into some active power output reduction and come back to pre-disturbance value within about 250 milliseconds, 300 milliseconds, which is fantastic. And the model does a pretty darn good job of matching reality there too. So kind of a double success story there that we wanted to share. And we've got a number of these that we're seeing across all interconnections, which is great. So we put out an alert. So we've had a couple of disturbances, the Blue Cut fire in August 2016, the Canyon 2 fire in October 2017. We're just getting ready to issue another disturbance report for April and May 2018 disturbances. And those disturbances looked very much like the Canyon 2 fire from October 2017. But after the Canyon 2 fire, we issued an alert seeking data on momentary cessation settings, transient overvoltage settings, to identify what's the extent of the condition out there and to recommend some mitigating actions to support BPS reliability. So I'm not going to go into a lot of detail on what we found, but the point that one of the big things from the modeling perspective that we found was that the vast majority of resources use momentary cessation in the existing models. Upon looking at those models used in the interconnection-wide base cases, do not accurately represent that control mode. So 9.6 gigawatts of 13.5 gigawatts are using momentary cessation, and I'd say very, very, very little of those are accurately representing that in the models. So that identified an existing modeling issue that needs to be addressed. Then we asked, well, can you make changes to either eliminate momentary cessation or mitigate its use by reducing settings, et cetera? And a lot of the geos came back and said, yeah, we can either eliminate it or modify the settings to make it more grid friendly, more grid supportive. We want those settings we want those changes to take place. So the method that we used in the alert was provide the proposed model. So the geo provides a bunch of data to the TP and the PC, not only what's out there today, but here's a model of what's out there today, and here's a proposed model of what we could change to. And the TP PC was intended to run studies and report back to the geo to say, yes, go ahead and make those changes. We've studied it. It's reliable. Now go and do that. Initial findings from this kind of third asterisk star over here, where the TP and the PC are reporting up to the regional entities and up to NERC on the findings that they're seeing in the modeling and the studies, were that the generator owners in almost all instances didn't provide models that were usable, models that accurately represented the data that they provided, and they definitely didn't provide proposed changes that were to be studied and to be approved. And so this feedback loop fell short, and we've identified that we have a modeling gap, we have modeling and studies issues, and we need to start instigating follow-up activities to ensure that the models are accurate. So we have some follow-up questions going out to the TPs and the PCs currently, seeking information on what are you doing to ensure that the data provided by the GEO on existing and future settings is accurate in your studies, is accurate in your interconnection-wide cases, and that those proposed changes are being administered by the GEOs. And so we're creating another feedback loop, kind of putting the onus on the TPPC to be engaging with the GEO to make sure those changes are being made, because that process needs to happen. It can't just happen that the GEO goes and changes a bunch of things that doesn't follow the FAC standards, it doesn't follow the mod standards. So the point here is that a lot more follow-up activities at the NERC level, both on the reliability side, standard side, compliance side, I'd say will be happening in 2019. So I'm going to pause there and kind of go a little bit more forward-looking, and I wanted to highlight some of the work that's been done on electromagnetic transient EMT type simulations. And Electronics and Andrew Isaacs have been a huge support of the NERC Inverter-Based Resource Performance Task Force, and I wanted to highlight some of the work that's been going on there, because it's really kind of leading us into the next phase of how do we interconnect high penetrations of inverter-based resources. So the first thing that I wanted to touch on was the model benchmarking, using EMT models to ensure that the positive sequence models are sufficiently accurate. And you can see here a fairly good match. You don't expect the EMT model to match the positive sequence model time step by time step because of different simulation techniques, different modeling assumptions, different controls are modeled, etc. But if you blur your eyes a little bit, you'll see that the oscillation magnitudes and the ring down of those oscillations match fairly well. The active power recovery matches quite well. The voltage dip during the disturbance matches quite well. And so this is a fairly good match. But the point here is that a lot of utilities are starting to demand that the EMT model be benchmarked against the generic positive sequence model to ensure that those models are somewhat reasonably matching, and that generic model is not a set of default parameters or anything. It's actually the equipment that's being used, because that EMT model is typically a very detailed, very accurate model. Another good example of the growing need for electromagnetic transient modeling is the whole concept of weak grids or low short circuit strength conditions. And we're headed towards a grid where we're seeing at least pockets of low short circuit strength on the order of a short circuit ratio of somewhere between less than 5, less than 3, less than 2, in some cases, less than 1.5. So we're not saying that the whole grid is going that way. We still have a large amount of synchronous machines. We don't see in North America headed towards a quote-unquote inertialess system or anything like that. But we definitely have pockets of very low short-circuit strength. And the question becomes, how do we know when we need to study those in more detail? Because the positive sequence simulations fall short in a lot of cases. They either don't diverge or they give results that don't match reality, mainly because there's a lot of complex controls built into these resources that aren't modeled in the generic positive sequence simulation tools. So this is a good example of a voltage excursion, a fault event, looking at does the resource provide sufficient write-through capability during the interconnection process. And it's not shown here, but the positive sequence simulation tool showed a very stable response. The fault occurs, the unit responds, comes back to pre-disturbance output in a couple hundred milliseconds, and off we go. But in reality, this is a fairly low short-circuit strength grid. The transmission planner knew that ahead of time, kind of flagged it and said, well, we need to probably look at this with electromagnetic transient simulations, and some PSCAD studies were initiated. And what we see was when the voltage drops, the unit responds with some reactive power, active power drops, and then the unit has a ramp rate coming back out of its ride-through mode. So as the active power starts to increase, the unit starts to experience some small signal instability, unit starts to oscillate, and the voltage, the POI voltage and the terminal voltages start to oscillate as well, and they hit a condition where voltage hits 1.2, which initiates ride-through mode again, and so the unit snaps back into drop in active power output. Voltages again recover, the unit starts to recover back out of ride-through mode, small signal instability occurs again, and the process reiterates. And so this is a good example of small signal instability, controls instability, control mode cycling, and none of this is picked up in the positive sequence simulation tools, the dynamics tools. It really requires some EMT modeling to be able to identify these types of things in some situations. But we're seeing a lot of modeling challenges all around. Good example there in the top, 2 models, one RMS positive sequence simulation, one EMT simulation, exact model, detailed representation, supposed to be exactly the same representation in 2 different software tools, and it was simply a parameterization error. So somewhere in that code, there was a per unit value that was set on the wrong base, and you get a vastly different response. Not much you can do from a planning aspect, but kind of shows the need to have that benchmarking. The middle plot there shows a good example of a DC line, studies around a DC line, and whether or not that HVDC circuit can maintain stability. The positive sequence RMS simulation showed that the unit goes unstable. That defined an operating limit. But when they ran the EMT studies, they actually saw, well, it's actually stable. It's able, at that current operating mode, the unit's able to respond and have a stable operation. But what the transmission entity did was they said, well, we're still going to rely on those positive sequence simulations to set the operating limit because we see instability there. So it's essentially a form of margin to say, well, we know it's stable, but it's sort of marginally stable and the tools are starting to fall apart. And so we need to have some buffer in there as a form of margin. And that's been sort of a recommended practice across the industry to build in some amount of margin to ensure stability, and they're using that in that way. And the bottom one there is just a good example of a mismatch. But in both cases, the PSCAD and the PSSE simulation, the unit was stable. And we're faced with these conditions where transmission planning resources are under very high pressure to interconnect resources in their queue, get those things online relatively quickly, and that's leading to cutting a lot of corners around modeling accuracy and model benchmarking. So we see there the blue plot and the green plot, vastly different responses. And in this case, the unit was brought online because both simulations showed a stable response. So model accuracy kind of falls as a secondary priority. And that, yeah, we want to get those models accurate, but we can do that once the unit's interconnected and we can ensure that the models match, and we can deal with that down the road because we know the unit will be stable under those conditions. Problem is you bring that unit online and then the transmission entity goes back to the generator owner and says, okay, now let's update those models. And we've heard a lot of anecdotal evidence that show that there's essentially they're not receptive to working on updating those models. They have a signed interconnection agreement. They're making money. They're producing megawatts. They don't want to be bothered, right? And they signed that agreement. So we need to have that upfront verification and benchmarking to make sure the models are accurate and that you have sufficient models to be able to run your studies, not only now, but 10, 15 years down the road. So if you think you're going to be in a condition of weak grids, you should probably plan ahead and plan to get those models necessary to run those weak grid type studies, even if you're not necessarily in a weak grid condition today. That doesn't mean everywhere we should ask for EMT models, but in some pockets where we think that might be an issue, we probably want to think about asking for that data ahead of time so we don't run into a crunch where we can't get that data. So looking forward, this is my last slide, but the question that I kind of pose is, do we need to rethink how we model and verify the models for inverter-based resources? So we know we have challenges with the modeling differences between the simulation tools, between the positive sequence RMS and the EMT. We need to kind of work as an industry to build our knowledge and our skills on EMT modeling. I ask a lot of transmission planning organizations how much time and effort and expertise they put into EMT modeling. A lot of times I get a head scratch. They don't know what EMT is. So we need to be kind of thinking, how do we ramp up those skills as an industry to be prepared for high penetration conditions if and when they come? Now, it doesn't necessarily mean everywhere is going to deal with these challenges, but we already have vast swaths of North American footprint with high amounts of either solar, wind, or a mixture of both. We seem to be headed that way regardless. We need coordination and guidance around positive sequence and EMT simulation approaches. We've been working at NERC. We have a guideline on low short circuit strength systems, what they look like, how to assess them, some potential issues that might arise, and mitigating actions to deal with those types of systems. I think that's just the first step in the direction of building expertise as an industry in the electromagnetic transient simulation realm. So I think we'll see a lot more work at the NERC level to try to support the industry to move the ball forward. Like I mentioned, we see changing grid stinks and not always sure exactly how to handle that. There are some physical solutions like adding synchronous condensers, adding transmission investments, etc. But there's also a lot of controls-based solutions that could potentially be a lot cheaper by working collaboratively with the transmission folks, the generation folks, and the equipment manufacturers to be able to handle those types of conditions. So that's always kind of option number one, is make sure you get everyone in the room, make sure that they understand the problem, and look at what are the real issues and what are potential solutions to those issues. The biggest thing I think is that the features that are coming out on the technology are well outpacing the generic model developments. And that's sort of expected in an industry that's under rapid growth like inverter-based resources. So things like quote-unquote synthetic inertia, no one really likes that term, but the inertia-based fast frequency response, fast energy injection type behavior that you can get out of some wind plants, for example, that capability, which is utilized in a number of interconnections around the world, is not built into the generic models. And so how you model that, you got to go to detailed user-defined models, etc. And the reason is just because that technology is sort of outpacing. And so as new features are getting added to solar and wind, we need to figure out, well, how do we deal with that the models may not accurately represent that, or even have the capability to represent that 2-5 years from now. So the question then becomes, do we have a growing need for the quote-unquote real code models, particularly for localized reliability studies, especially for EMT type simulations? So should we be taking the physical code that's actually in those inverter-based resources and plugging those into detailed models that are used for the EMT simulations? And anytime any code gets changed in an inverter-based resource, that flags that the model needs to be updated accordingly. That's been used successfully in some parts of the world. We have an IEEE task force that's looking at driving that forward. And in some ways, at the NERC level, we're trying to support that activity and try to overcome the simulation challenges, the tools, capabilities challenges, and then also hear from the manufacturers and the equipment owners, is that something we want to do and how do we get there? But it seems like we need to be doing something, and I think that's where we may be headed, at least as a longer-term vision, to overcome some of the challenges we have with high-penetration generic models in the case. So lastly, I guess I'll just mention there's a lot of activities going on, especially at the NERC level, but around the world. But we have guidelines. I recommend you take a look at those guidelines if you haven't. We have the IRPTF, the PPMBTF, SAMS, our new system planning impacts of DER working group. NERC and the ERO enterprise, particularly with WEX, has done a number of disturbance investigations looking at what happened, what are the causes, what are the key findings and the recommendations, and those are leading to NERC alerts. We have the new P2800, so if you're not familiar with the new IEEE project for P2800, it's sort of a mirror image of 1547, but for the bulk grid. So can we develop performance and equipment specification standard for inverter-based resources connected to the bulk power system, since we don't have that in North America today? So I highly recommend getting involved with P2800. NERC has taken a fairly substantial leadership role and support role in that activity, so we're going to be trying to push that forward relatively quickly. And then, like I mentioned, just a lot of industry activities going on at NERC, ESIG, and a whole bunch of others around the world. So key push here is to get involved, reach out to Charlie, Bob, myself, and we'll make sure to get you in touch with the right folks. So with that, I'll turn it back to Charlie.
Okay, Ryan, thank you very much for a very comprehensive walk through the standards landscape. So we've got time for a few questions. There's been some questions coming in. If you have questions, feel free to submit them through the question and answer box. Some were submitted early in the webinar, and there may be already answered, but I'll ask it anyway just for clarification. One is First question, Ryan, as part of Mod 32 compliance, is the generator owner required to submit only generic dynamic models, or are UDMs accepted? I'm not sure what UDMs are.
Yeah, so UDMs are user-defined models. So Mod 32 is a standard that essentially just says the transmission and planner and planning coordinator need to jointly develop a set of modeling requirements and data reporting procedures. And that's essentially all the standard says. And then there's an attachment that kind of explains what should be included in those. So that gives capability to the transmission planner and the planning coordinator to define whatever they want in terms of what is acceptable from a level of detail, from the types of models, the acceptable list of models, how those models get reported, etc. At the NERC level, we've been trying to drive some consistency around the TPs and the PCs to provide the same to ask for the same types of data. We're working on that right now. But in essence, it's up to the TP and the PC to define and prescribe what is required for the GO to submit and how. So in a lot of cases, that is dictated by what we call Mod 32 designee. So you can think of WEC, Texas RE, and the ERAG MNWG. They develop the interconnection-wide case creation process. The planning coordinators are required to meet that process. And in all interconnections, maybe not Texas, but in all the other interconnections, that requires generic models. So that doesn't preclude someone from saying, I want a generic model, and you can also provide a user-defined model for localized studies. Both options could be an option, but the planning coordinator will find itself in a crunch if they don't also require a generic model, because that's what's required by the designee to build the interconnection-wide case. Texas is a unique situation, a smaller interconnection with a very rigid process, and so I think they allow some user-defined models in a lot of cases. But in the East and in the West, it's up to the PC and the TP to define what they want, and the GO needs to meet those requirements.
Okay. Here's a very specific question. Are the dynamic models required in PSSE version 33, or is version 32 acceptable?
That's going to be up to the local utility and the transmission planner, planning coordinator, all the way up to the Mod 32 designee. So refer to those folks for that information.
Okay. And are there specific parameters around what constitutes a match between the model and the response?
Yeah, that's a touchy subject, and Bob, feel free to jump in here if you want, but I can take a first crack at it. Different parts of the world have a different opinion on what constitutes good enough for a match. Some parts of the world dictate numerically how well a simulated response needs to match an actual response. That was faced with a lot of contention and challenge, particularly from some of from the manufacturers, the OEMs, but as well as the generator owners, because there needs to be, at least in my opinion, some flexibility in what constitutes a good match. So like I was talking about earlier, if you've got a response that generally matches quite well, the dynamic response is very close, the active power ramp rate is close, the oscillation recovery is close, the voltage dip is matching really well, you would generally call that a good match. It's a reasonable representation of the equipment that's installed out there in the field. You may get some numerical, swings or something on the first. You may get an initial spike caused by a numerical issue in the simulation tool. And in a lot of cases, you can discredit that or ignore that because you can attribute it to either a simulation artifact or something along those lines. Doesn't necessarily mean that model is bad or not usable. It means that it may have parts of that simulation where it sees a match that doesn't, or a response that doesn't really match reality. So going to a numerical-based calculation of how good is good enough is really not a good approach, in my opinion. And we've asked a lot of folks that have done testing for many years, and the vast majority of them agree that going to a numerical-based what's good enough is not really a good approach. Nor is a curve-fitting approach where you just try to fit that model to match reality without looking at what's actually being set in the parameter values. So hopefully that provides a little bit of detail.
Okay, Bob, you want to chime in on that before we have to close out?
Well, I agree with Ryan. Going back some years during the development of the generic models, there were folks from Europe especially that were engaged in that effort, and then this whole validation issue came up. And the Europeans saw it, that it needed to be analytical and somewhat academic, and the folks participating from the U.S. pushed back on that quite a bit. The last thing I'll add is that if we're talking about field data, post-event data that's been recorded, it's actually a situation where we're not going to have clean events. So trying to get too analytical and quantitative with the validation, I think, is you're not going to come out ahead on that one too often.
Okay, we're still got a lot of questions left, but I'm going to have to wrap it up here. It's the top of the hour. As I mentioned earlier, there's an email going to go out once the presentations and the audio file have been posted. I want to encourage you to send any follow-up questions to info@esig.energy, and we'll get them answered along with the ones that we weren't able to answer that have already been submitted and get them posted. Or you can just reply to the email that Ryan Willis will send you with the announcement of the posting of the webinar. And please do look for the SurveyMonkey email with some additional follow-up questions for you to provide information. It'll be helpful to Ryan and to NERC for guiding some future activities in this area. We appreciate your engagement. Look forward to seeing you at our next webinar on Wednesday, January 23rd at 2 p.m. That webinar will feature Mahesh Morjaria from First Solar and Arnie Olson and Jimmy Nelson from E3, and it will cover the topic of the economic value of flexible solar power plant operation, which is also a very timely topic on the national scene, given the proliferation of PV power plants. So we hope to see you there as well. Further information on all of the webinars and meetings can be found on the website at www.esig.energy under events and in our newsletters and informational emails. So Bob and Ryan, I want to thank you again for this very timely and informative webinar, and thank all of you for your participation. We look forward to seeing you again next month, and in the meantime, thanks again and happy holidays.
Happy holidays, folks.